A pleasant greetings to all. In this video, I am going to explain about single line to ground fault. Method of symmetrical components is used to resolve unbalanced system into a balanced system. Why we go for symmetrical components? The majority of faults in power system are asymmetrical. To analyze an asymmetrical fault, an unbalanced three-phase circuit has to be solved. The direct solution of such a circuit is very difficult. The solution can be more easily obtained by using symmetrical components. So that's why we go for symmetrical component analysis. Here I am going to explain about single line to ground fault. So this is the diagram that shows the single line to ground fault. So figure represents three-phase synchronous generator with neutral ground through an impedance Zn. Suppose a line to ground fault occurs on a phase A. This is phase A. Line to ground fault occurs on a phase A through an impedance Zf. Assuming the generator is initially on no load, the boundary condition at fault point are. Here this is the voltage Va. The current flowing through is Ia. The generator is on no load condition. So Ib equal to 0 and Ic equal to 0. Next I am going to write the boundary condition. What is Va? Va equal to Ia into Zf. See, Va is the voltage. The current flowing through the impedance, that is fault impedance is Ia. So Ia into Zf. What about Ib and Ic? Both are equal to 0. Next, I am going to find out the symmetrical component of the current Ia. Actually, three symmetrical components are there. The first one is zero sequence component of current. This is the positive sequence component of current. This is the negative sequence component of current. That is equal to 1 by 3 of 1, 1, 1, 1 A square, 1 A square A. And here I am going to write the first one is Ia and second write Ib and next write Ic. And what about Ib and Ic? Ib and Ic equal to 0. So from this equation, once again I am going to write this equation Ia0, Ia1, Ia2 that is equal to 1 by 3, 1, 1, 1, 1 A square, 1 A square A into Ia 0, 0 because Ib and Ic equal to 0. From the above equation, what is Ia naught? Ia naught equal to Ia by 3. What is Ia1? Ia1 equal to Ia by 3. And what is Ia2? Ia2 also equal to Ia by 3. So, three currents are equal. Ia0, Ia1, Ia2 all are equal to Ia by 3. And next I am going to write the phase voltage Va in terms of symmetrical component. So, Va0 plus Va1 plus Va2. Okay. So, here this is Va0, Va0 and this is Va1 and Va2. Now, I am going to add these three together. So, what about Va? Va equal to, what is Va0? 0 minus Z0 into Ia0. The suffix you have to write. Then Va1 is Ea minus Z1 into Ia1. And last one is minus Z2 into Ia2. Now I have to add all the three. Va equal to Ea minus all the currents are equal. Ia0, Ia1, Ia2. Three currents are equal. So how to write? Z0 plus Z1 plus Z2 into Ia0. I am going to write like this. So this is the phase voltage VA. So after getting this answer, I am going to substitute the VA value. So what is VA? VA equal to ZF into IA. So ZF into, what is IA? IA equal to IA not equal to IA by 3. So what is IA? IA equal to 3 into IA naught. So I have to substitute the value here 3 into IA naught. So now instead of VA, what I have to substitute? 3 into ZF into IA naught, that is equal to EA minus Z naught plus Z1 plus Z2 into IA naught. So from this equation, EA is equal to 3ZF IA naught plus Z naught, Z1, Z2 into IA naught. So how to write EA equal to, take IA naught outside. So inside we are having Z naught, Z1 plus Z2 plus 3ZF. So from this equation, I am going to find out what IA naught. So IA naught equal to EA divided by Z1 plus Z2 plus Z naught plus 3 into ZF. Now what is the fault current? How to write the fault current? IA equal to 3 into IA naught. So 3 into EA divided by Z1 plus Z2 plus Z0 plus 3ZF. So this is the equation of fault current. Now we have to represent the fault current in terms of all the sequence component. Generator voltage and the sequence impedance, that is positive sequence impedance Z1, negative sequence impedance Z2 and zero sequence impedance Z0. ZF is the fault impedance. So after finishing this, we have to draw the sequence network for this single line to ground fault. How to draw the sequence network? See here, Z1, Z2, Z0 and 3ZF all are connected in series. So I have to draw like this. Sequence network for the single line to ground fault. Sequence network for single line to ground fault. I have to draw like this. The first network is the positive sequence network. Z1. What is the current flowing? IA1. Here this is the positive sequence network. Okay, I have to draw like this. EA. And next I am going to draw the negative sequence network. The negative sequence network, we are having the negative sequence impedance only. There is no voltage. And next I am going to draw the zero sequence impedance Z0. Here there is no voltage. And what is the current flowing here? The current flowing is IA2. Here the current flowing is IA0. And what is the voltage across it? The voltage across it is VA1. This is the positive sequence voltage. Here VA2, negative sequence voltage. And here VA0, zero sequence voltage. And again, one impedance is connected. That is also connected in series. So then I have to do the connections. So all the impedances are connected in series. So how to draw this? So this is connected in series. Then these are connected in series. And finally This is connected in series, that ZF. ZF is the fault impedance that also connected in series across the voltage EA. So once again I am going to write the fault current IA equal to EA, that is 3 into EA divided by Z1 plus Z2 plus Z0 plus 3 ZF. That's all. Thank you. Have a nice day.